Okay, so let's start by having you pause the video and try each one of these problems in the warm-up, and then go ahead and check your work. Here we are solving each equation for y. So because I want to get y by itself, I'm going to subtract 2x from both sides. So on our first one, y is going to equal 3 minus 2x, or you could have negative 2x plus 3. On our second one, we want to solve for y, so I'm going to add x to both sides. But then I have to divide each side by 3. So y is going to equal negative 2 plus 1/3 x, or we could have 1/3 x minus 2. And our last one, I'm going to subtract 4x from both sides. Then I'm going to divide both sides by negative 2. So y is going to equal negative 4 minus, or plus, because it's negative divided by negative, 2x. On this last problem, we're just generating ordered pairs for y equals 1/2 x plus 1. So the easiest way I think to do this is just create a table. So I'm going to do negative 4, negative 2, 0, 2, and 4. Half of negative 4 is negative 2, plus 1 is negative 1. Half of negative 2 is negative 1, plus 1 is 0. Half of 0 is 0, plus 1 is 1. Half of 2 is 1, plus 1 is 2. Half of 4 is 2, plus 1 is 3. So in today's lesson, really what we're looking at, and the reason that we're doing that warm-up, is we are learning how to graph functions given any type of domain. So in our first example today, we are given the domain negative 2, negative 1, 0, 1, and 2, and we are putting it into the function f of x is equal to x to the second minus 3. So here, when we put this in, our x value is the domain, remember, and in this case negative 2 to the second power was 4, minus 3 was 1, so our ordered pair would be negative 2, 1. In our second one, we have negative 2, negative 1 to the second power. Notice I'm putting that negative 1 inside the parentheses because they're squaring that whole thing, minus 3. So negative 1 to the second power is just 1, minus 3 is equal to negative 2. So ordered pair is negative 1, negative 2. And then we have 0 to the second power minus 3. So this is going to be 0, negative 3. Now let's do it for positive 1. So we have 1 to the second power minus 3. So 1 to the second power, remember, is just going to be 1. Minus 3 is going to be negative 2. And then when we do 2 to the second power, that's 4. Minus 3 is going to be 1. So our last ordered pair is 2, 1. So now that we've figured out our ordered pairs, we're going to just go ahead and graph those. So our first one is negative 2, 1. Then negative 1, negative 2. Then 0, negative 3. Then 1, negative 2. And then lastly 2, 1. And then one thing that I want you to notice is that not everything we graph will be a straight line. In this case, we have more of a V or a curved function, which you'll learn more about later this year. Alright, so now I want you to go ahead and try this one out on your own. So there's a couple different ways you could do this. One of the easiest ways, though, is to actually solve for y like we did earlier, which I'm going to go ahead and do. I'm going to add 2x to both sides. So now y is equal to 2x plus 3. And then I'm going to go ahead and just create a table using the domain values that they've given us. So negative 5, negative 3, 1, and 4. So negative 5 times 2 would be negative 10, plus 3 would be negative 7. Negative 3 times 2 would be negative 6, plus 3 would be negative 3. 1 times 2 would be 2, plus 3 is 5. 4 times 2 is 8, plus 3 is 11. Now if you notice here, these points are already graphed and they form a line. One thing to keep in mind is that if the domain of a function is all real numbers, any number can be used as an input value. This process will produce an infinite number of ordered pairs that satisfy the function. Therefore, arrowheads are drawn at both ends of a smooth line or curve to represent the infinite number of ordered pairs. If a domain is not given, assume that the domain is all real numbers. So if they ever just give you an equation to graph, you have to assume that the domain would be all real numbers and you could put in any value. So when we're graphing functions using a domain of all real numbers, you're going to use the function to generate ordered pairs by choosing several values for x, and you're going to plot enough points to see a pattern for the graph, and you're going to connect the points with a line or a smooth curve. So why don't you go ahead and pause the video and try this one out for yourself. So first you want to go ahead and pick values for x. I like to pick a variety of negative and positive. So if we start with negative 2, I might use negative 1. I always like to use 0, 1, 2, and 3. Because I like to keep numbers fairly easy to work with. Plus if you think about a coordinate plane, normally we're working in that inside piece anyway, so you want to be around the 0. So here we have negative 3 times negative 1, which would be 3, plus 2 would equal 5. So our ordered pair would be negative 1, 5. And we have negative 3 times 0 plus 2 would be a value of 2. And we have negative 3 times 1, which would be negative 3, plus 2 would be negative 1. Then negative 3 times 2 would be negative 6, plus 2 would be negative 4. And then we have negative 3 times 3, which would be negative 9, plus 2 would be negative 7. Then the second piece you would do is plot enough points. So you can see that our points are already plotted here for us. And then if the ordered pairs appear to form a line, we're going to draw a line through all the points to show that the ordered pairs that satisfy the function, and we're going to make sure we draw arrows at the end. Alright, so my line there isn't really, I'm just going to draw it through. Usually you want to use a ruler, and then notice I'm going to put arrows on the end. So now remember, this actually represents any ordered pair that would be a solution to that function. So let's look at another example. Here g of x is equal to the absolute value of x plus 2. And we're just going to create a table and pick several values. So I'm going to use negative 2, negative 1, 0, 1, 2, and 3 again. Absolute value of negative 2 is 2, plus 2 is 4. Absolute value of negative 1 is 1, plus 2 is 3. Absolute value of 0 is 0, plus 2 is 2. Absolute value of 1 is 1, plus 2 is 3. 4, and then we'd have 3 plus 2 is 5. Now once again, you'll notice that our points are already graphed. Now here we're going to draw lines, but you notice that there is an end, so it almost creates a V function. So we're going to draw lines through all the points and draw arrowheads on the ends of the V. Things to remember that in real world situations you may have to limit the domain to make your answers reasonable, even if the equation itself does not. So for example, quantities such as time, distance, and number of people can be represented using only non-negative values. So in both the domain and the range are limited to non-negative values, the function is going to be graphed only in quadrant number 1. So now let's look at a real-life application of this concept. So a mouse can run 3.5 meters per second. The function y equals 3.5x describes the distance in meters the mouse can run in x seconds. So we're going to generate a table. So now in this particular situation, it doesn't make sense to use a negative because we can't have negative amounts of time. So our lowest that we could have would be 0. And then we'd have 1, 2, and 3 seconds. So now we're just going to have 3.5 times 0, which would be 0. So our ordered pair would be 0, 0. Then we'd have 3.5 times 1, which would be 3.5. So our ordered pair would be 1, 3.5. We have 3.5 times 2, which would equal 7. And then finally 3.5 times 3, which gives us 10.5. So our last ordered pair would be 3, 10.5. Now here we have already graphed, and you notice there's a line, but at this end, at 0, 0, there is not an arrow on that end because negative values, we said, don't exist in this situation, so our graph actually stops there. Now we're going to use the graph to estimate the distance and the mouse runs 2.5 seconds. So what I'm going to do is I'm going to go over to where 2.5 would be in our time. I'm just going to follow that up until I meet the graph. Now here it's a little bit below our 9-second mark, so we would estimate that it would be about 8.75 seconds, or 8.75, see, it wouldn't be seconds, 8.75 meters, because we're talking about the distance that the mouse could run in 2.5 seconds. And I just got that by using the graph of the line and then drawing straight up to where I needed to be. If you don't have any questions, then you can go ahead and get started on your homework.